So the next talk is mine, and there is nobody to announce me. So I'll jump straight in. So my name is Dmitry. I'm here as the moderator today. I'm very happy to be here as well and to help organize this conference and actually work as a Rust engineer, Rust web engineer, and C and all this stuff in LightSource. It's the company on the back of your t-shirts. But I'm really excited about OCaml. You can say this by looking at my keyboard. Yeah, I know how to hide it. But basically, yes, I'm doing OCaml for a quite long time, mostly for our pet projects in open source and some kind of freelancing. But today I'm gonna be talking about a library that I've been doing for 4 years already. Oh God, time flies. And it's a library for image comparison. This is 2 images, 2 screenshots of FUN OCaml page, just to let you know what it is actually in fact. And I'm going to blame Sabine a little bit. So at some point, we updated speakers, volunteers, avatars, and there was a wrong URL. And basically, you can see there is clearly a bug. On the right image, there is no my face. So odiff can catch that quite nicely and just show you an image difference exactly between two images. And this is important to understand what we are trying to do and what we're trying to build the fastest in the world. Because odiff claims to be the fastest in the world. To be honest, there are not that many competitors, but there are competitors written in C++, in Rust, kind of. It's not a valuable comparison, but in fact, I claim my project to be the fastest in the world, and it's written in OCaml, and it's kind of successful. Basically, we have more than 2,000 GitHub stars. The project is alive; it is not dead, which is, I think, for a OCaml project is kind of nice achievement. It is used across 8 different languages. So basically, people are using OCaml from Java, from Rust. Yes, it's my project, but who cares? From JavaScript mainly, and there is 4 SaaS visual regression services, which is basically a service which takes your screenshot from different builds and compares them. Are built around odiff. 2 of them are publicly announced that, 2 of them not, but I know. And basically, they build a business around my library. So today I'm going to tell you a story about how this project started, how it became faster, what the optimizations I did, and maybe you can do to make your OCaml projects faster and to be fine. And I'm not trying to be pretend to be a main character, but we start with the very start. So at some point of time, I've been working at Cypress. It's a visual. I've been working on Cypress and at Cypress as a company. It's a visual regression testing. It's a JavaScript testing framework, end-to-end testing framework, which tests how JavaScript web apps execute it. And basically, we had a problem. The CI of Cypress contains dozens of thousands of Cypress tests, but for some reason, running dozens of thousands of Cypress tests was slower than running around 1,000 screenshot tests. We've been using Percy. Today, the image is totally different, but in fact, I tried to build something to optimize this madness because I was literally 30 minutes waiting for the easiest stuff. And I built it, and I published it, and I get a lot of questions. Why didn't I start building in C or Rust or Zik or C++ or whatever? And there is quite a few answers to that. Firstly, I did love OCaml by the time. I've been using OCaml a lot, and I knew OCaml, but I've been using C as well, and I've just tried to make something amazing and something useful in OCaml. There is more, practical reason why I did choose OCaml, because if you remember, there was a project called Fastpack. Maybe not a lot of people remember it, but in fact, this project was basically an alternative to ESBuild, which packs and bundles JavaScript. And at the very start, it was actually faster than ESBuild. But for some reason, ESBuild did grow a lot of hype, attention, and all of this stuff, but Fastpack just died. But inside of the Fastpack, the maintainers of Fastpack have been using Easy. Just raise your hand. Do you remember the Easy and all of the reasonable things and hype? And in 2020, it was like a big thing. It was a big thing. It was a new, shiny, glowing, cutting-edge technology that I wished to try. And it was, oh my gosh, sorry, my clicker. And I've been using all of this new stuff, and the Reason ML for native. It was written in Reason originally. I've been using libraries that are all dead right now, basically. And I thought that it would be a nice idea to write something that targets primarily JavaScript users in Reason, because it kind of closer to how JavaScript looks, but we didn't get any contribution from JavaScript, so it was useless. But in fact, I started building it one more reason, because the Easy provided the only way, the only framework, the only build system on Earth was providing NPM package, ability to build OCaml native binary into NPM package and publish it straight to NPM. It was actually the easiest way. I didn't think at all about all of the problems, all of the building, all of the infrastructure, publishing stuff. I was doing the shit, getting work done. And it was amazing, because OCaml tooling usually gets insults about how poor infrastructure is, but this was amazing. And I loved the project. It was really ambitious, but unfortunately it gets literally lack of support right now. And I've been starting doing this by taking up the paper, the research from the scientists about how to compare images, and I won't told you how exactly we need to do, but this is basically the paper describes how to formally represent this meme, right? So we don't need all of the colors to be compared one by one, number by number, because some of the colors are very similar. So we want to get some threshold and compare colors one by one, but within threshold. So little anti-alias pixels are not visible that much. So how to build it? So we built the code, I built the code, and it was faster. It was faster than JavaScript implementations, but it was not amazingly faster, for sure. And I started profiling it. And here comes a very, very interesting details that I'm going to show you. But I'm going to start from the benchmarking. And benchmarking is hard. Benchmarking is a very complicated stuff. This is an instrument SAP on macOS, which you can use, but this is basically an alternative to perf tools on Linux, which I've been using. And yeah, this is a very rare thing, rare scenario when GUI app is actually better, in my personal opinion, than the perf tools. And if we will break it down, you will see actually, like, you just run the perf, and then checking up how much time something was executed. Here's a breakdown by the functions. You will immediately see it, and I started doing the thing a lot. And you can start immediately see this is one of the latest runs I did for odiff, and you can see that garbage collector took less than a millisecond, because the resolution is millisecond. People are usually saying me that I'm dumb because I try to make something fast with garbage collected language, but as you can see, in odiff, garbage collector basically doesn't work. Then you can see here are all of the C functions that were called. And this is kind of a very exaggerated example. You usually want to give some really, really long input so the measurement error does not affect your measurement. And I did a giant mistake originally that I've been not looking into these giant numbers. I will be talking about this a little bit more detailed, but I basically was optimizing this start function, which is an entry point to your OCaml program. And you can see that out of how much? 584 seconds, the OCaml code works only 230 milliseconds, which is kind of impressive. And it's working, it takes so few times because it is optimized. So how to optimize the OCaml code? I will walk you through one simple example. This is NeoVim, by the way, that represents how you can spot and fix the inefficiencies. This is kind of exaggerated example. I am sure if you read this, you will find a performance optimization, but I promise you there will be a plot twist. So let's break it down. So you can see here, you can see a module that has some kind of abstraction around how the image is represented. It has some pixel type, and it has the read pixel function. So important part, these modules, there are different modules for every image format, and you usually have one type in kind of MLI file and something like that, and you basically take your function and implement it. So you have kind of decoder, it doesn't matter right now, you take a pixel from decoder, then you get every individual value for every individual color. It's RGBA, yeah, for PNG, and for sure, like A will be like 255 for every JPEG file, but it doesn't really matter. Then you are creating a tuple of 4 elements within this function and return it. Important part, this is implemented like in one project, right? You're trying to be a good developer, right? You're trying to separate the conceptions, you put this into some other file or some other project, you separated it, and then in some other file where you actually do comparison, you read 2 pixels from image 1 and image 2 that you're comparing, and you compare the pixels, and then you do all of the massive comparison because it's a quite large formula, and you want to firstly check if the pixels are actually equal, and if equal, we skip the calculation step. So I know that somebody might see the issues here, but let's actually break it down. And I will show you a few assembly slides of ARM assembly, but please don't run away. I will try to be as descriptive as possible and to break it down as much as I can. So let's zoom in a little bit. Can you see it? I hope so. So here is what happens. On the very top, you can see a call of the C function, which called caml insert32 to float unboxed, which is actually doing the unboxed float stuff. And on the right side, you can see this function is basically one instruction. And it's basically one instruction assembly that basically takes V0, which is inserted to view of the register, and turns it into D0, which is a float register, and returns that. Basically, that's it. And it's literally unboxed float. But don't please buy it because, you know, unboxed, it is unboxed now, but it changes. Here you can see a very representative pattern of the OCaml heap allocation, which is something you likely read in the documentation that OCaml is not doing a strange like mem maps on every heap allocation. Everything that it does to allocate a minor heap is basically decreasing the pointer, which you can see right on the machine. This is a heap allocation in OCaml. It's 2 instructions. It's just 2 instructions. It is much faster than in Rust, but yeah, for sure at a different cost. So you can see that we are taking the x27. This thing is the pointer to the minor heap, and we decrease the pointer by the amount of memory we want to allocate. In this case, it's 0x30. It's 48. It doesn't matter. But basically, and if the comparison, and then we compare in this value to the limit of the heap, of the minor heap, and if the limit is reached, we go and call garbage collector. This function, this nonsense in the end of the b.allow is basically caml call gc function. So, important thing, it might not be called, right? If we don't reach the limit, the garbage collector is not called. This is the important part. Let's go next. Here you can see, shame, a little bit of inefficiency of the OCaml compiler that adds 2 registers consecutively. What does it mean? It means that you do x19, so you do something like a equals b plus 8, and then you call a equals a plus 32 instead of a plus 40. It's an efficiency that you will see if you will start doing this thing. You will start noticing this inefficiencies in generated assembly by OCaml very often, because OCaml doesn't use any kind of LLVM intermediate representation. So basically, it just compares direct instructions into the direct, functions into direct instructions. So it does not optimize the assembly. But at the same time, it's kind of really fast. So it's not a big deal, to be honest. Now you can see repetitive patterns, and when you do this kind of investigations, you usually look for these repetitive patterns. So here you can see that we allocate 4 constant register. Again, in efficiency, it could be 1 register in this case, that is using just 1 tag. So this 0x4fd, it's a tag for floats in OCaml. And then basically you can see that it takes this x19, which now holds the pointer to where we want to put our floats, and it puts the floats, the D register is a float, into this into the heap, and by the -8 it puts the tag, right? So we see the repetitive pattern for heap allocation and tagging allocation in OCaml. It's very, you start looking into OCaml code differently when you do the things. And now I basically scroll down. So this is one function. I left this, y dot, so you do believe me. And now you can see that there is a fourth float allocated on the top. For some reason, it does another heap allocation in this function. And it does allocation for another, I don't know, a lot of bytes. And it takes another, the same thing, another heap allocation, another, an efficiency of adding 2 pointers one by one. Now it adds fourth float to the new allocated memory. For some reason, it put 3 first float into one portion of allocation and 1 float into the other portion of allocation. And now it basically allocates the tag for the tuple, which is 0x1000, and puts all of the 4 floats to the heap, to the tuple. So what we can see here, that we do boxing the floats, so we do 2 heap allocations, and we put the floats to the allocated heap. Efficient? It doesn't, I don't think so. So how to optimize it? We can optimize it, and I'm sure you know how to optimize it, maybe, likely. So if we are talking about optimization, we can do, CAML records that only have floats, just floats, are unboxed. So instead of doing this, instead of doing tuples, you change it to be a record, and you do the same total thing, right? You read the pixel, and now you compare in the pixel, and you basically optimize it. And it's definitely optimize it. You will see the difference. You will see the difference. Let's break it down again. So here you can see the last, so it now allocates all of the unboxed float to be kind of like at register values. I just don't have space to do this. So it's the last one. Now it allocates one time 5 bytes, yes, 5 bytes on a heap. Again, 2 instructions. Now it doesn't do this nonsense with double addition for some reason. Now it allocates the tag for purely float record in OCaml, which is important. And now it basically takes and puts firstly the tag to the -8 shift, and then puts all the 4 floats on the heap. Much more efficient. And you might think that we did a well-done job, right? We finished the optimization, and everything works kind of good right now. Some of people who don't actually care about real performance and don't understand how a computer works will start praising themselves, like boasting their superiority, making blog posts on Twitter, complaining that our CAML compiler is the not efficient compiler. But in fact, you didn't do nothing. If you will run the performance, you couldn't just skip it. It says 40 instructions, and the heap allocations are really fast in OCaml. So it's just literally unnoticeable. It will be noticeable, but it will be like 10 seconds versus 9 seconds, 900 milliseconds, something like that. So what we need to do to be, oh yeah, I have this funny meme about stack and heap, all of this, debates about how stack and boxed values are different. They are both just memory. They are both just memory. And when you have once allocated a heap, your heap allocation is 2 instructions. Why would you care about this? What we should care actually about is this 598 instructions being repetitively repeated by a lot of times. A lot of times. So, can you hear me well, by the way? Perfect. Because I just heard the difference. So, what should we do? Let's actually think about what we're trying to optimize. Sorry? Like this. This is better. Yeah, I will try to hold it. Sorry. So, these microphones are really uncomfortable to hold. This is so ridiculous. So, what we need to think about is what we actually need to optimize. So if we will take the FUN OCaml, the latest screenshots, which is not the largest landing page I can find on my big laptop screen, there will be 45 millions of pixels. 45 millions of pixels. And if you want to compare pixels one by one, for sure you will do things like unrolling loops and so on and so forth, but you need to understand what you can eliminate, which unused work, which useful work, useless work are you repeating in every iteration of this loop. This is very important. And the biggest, observation that you can think of, that the pixels, so we do target most of the people. So yeah, just let's think about this. Use case. Would you compare two different pictures with odiff? Like just two completely different pictures? I bet no, right? So pictures are mostly always same. If you took screenshots, 99% of the time they will be equal. And sometimes some text will be different, something else will be different, something even like some small details will be different. Like 1% of time, maybe 0.1% of change. And this is important because when we're talking about the previous implementation, and we will actually see what happens inside, that you do all of this work within unrolled loop. Okay, it's unrolled, everything is okay, tail recursion optimization, so on and so forth. But then you did one simple comparison, which kills it, which basically kills it. So if we'll take a look on this function in OCaml compiler that runs the comparison, you will actually see that this is not the big function. And what it's doing is basically calling another function, which loads the data from two boxed values and compares them one by one. It's a polymorphic function, so it is not optimized. It doesn't load directly those floats. It does. It is just inefficient. This part is inefficient. And here are two just super interesting things I just want to share that I found really interesting, that OCaml, like this kind of profiling and investigating can teach you. Like, first of all, I've been tweeting about this, but you can see a clear representation of the booleans in OCaml, which is equals to 3, because of every boolean is a native int, which shifted to the left. But this is not an interesting thing. The interesting thing is here. So basically, in case values are not equal, what we're doing, we're taking either x or 0 plus 1. And in ARM assembly, it's one single instruction, which, like, I thought that, yeah, I just found this an interesting optimization because I thought that ARM should be reduced instruction set. But in fact, such a useful operation like condition not equal x or x plus something could be done in one single instruction in assembly. This is super cool, even though this is not OCaml compiler produced. But be honest about this is C code. So what we need to do, actually, we need to firstly break it down, and we need to find a way to get not like the RGB pixels, but a base, the most, like, the most starting representation of the pixel that decoder takes, and compare it. So basically, we're taking raw pixel from our decoder of images, and then comparing not an OCaml representation values, but in32s. And it actually helps. So now you can see, this will be one of the last slides with assembly. You can see here, it's an actual odiff code. And in odiff, we do support different image types. So you can, for example, compare PNG to JPEG, for instance. And now you can take these functions are called as closures. You are taking them, you're loading these functions. Now you do some kind of LDRs loading from registers, but this is okay because we do this. They are likely will be an L1 cache, which is totally fine. And now we do one simple comparison of ints. One simple comparison of ints instead of this 600 or 800 registers. We don't do a heap allocations in 99.99999% of time. And this what actually will make your code different. So, like, what could we learn about this? In order to make your code actually fast, you need to make your code worse. You need to make your code simpler, especially that OCaml compiler does not do a lot of optimizations of the low level, so you need to tell your compiler how to optimize your code. It's actually important. Just sometimes you will need to not use options, but use some Boolean flag. Sometimes you will need to repeat yourself. But important part that you need to do something, and to usually makes your code worse, but it kind of makes your code much more efficient. So a little note about GC tuning. We do this settings. I just want to throw it out to the world. We allocate 16 megabytes of heap on a 64 machine. And this is kind of experimentally set options that helps odiff to use garbage collector as few times as possible. We can debug it with space-time, but it doesn't really work on our machines properly. So I basically just do measuring it using GC stat, and you can see that during the really, really big comparison, it just do 80 minor collections, which is one go, and it's fine. No compactions and 6 major collections, which is under 1 millisecond on my machine, which is good. So we optimize it. So let's get back to the story. We optimized the image. We did a lot of nice work, and we published the project. So we get the project, and we get a lot of attention. People started using it. Everything goes very well. I'm super excited about it. But one day you see this surprise. Basically, yeah, I'll read it out. And somebody made a project in Go that says faster than the fastest in the world, basically comparing to my project. Should I tell you that this wasn't the best day of my life? Yes. So, but they a little bit cheated. So basically, when I open the sources, you will see that they do the multiplexing by course, and there was time before OCaml v5, and they basically split the load across the course. And when I removed this line, I found that it is like not 0 to non-performance difference. Sometimes OCaml odiff will be faster, sometimes Go will be faster version. I found one interesting detail in a few slides, but just a little bit note on parallelism and why parallelism is actually not helpful in this case. So imagine how odiff is actually used. So it is used from the test runners, from the end-to-end test runner, which runs a lot of tests and runs a lot of comparison, or within regression service, which loads the balance on itself. There is no reason to put, split this giant loop of comparing every pixel between course, because it comes with its own cost to do this, primitive stuff, counting, and all of this stuff. You need to do the atomics, you need to do whatever to make it actually splittable, and it only will help to reduce the time in benchmarks. I don't think people care about benchmarks. Benchmarks are useless. You can run them yourself, but what people care about is actual performance. So there is no reason to do this even now when we support OCaml v5, but maybe I will do this just to show out that OCaml is even faster. So what I really found after this project pops out, that we have one little inefficiency. And thanks a lot to the author, Nikita Tolkachev, of this project, because he actually helped to find it. I found that the image decoding in Go takes much less time. And do you remember I've been talking that I didn't look into this function? That was actually a giant mistake, because you should optimize whatever actually takes much more time. Because in fact, I've been using camel images by that time. Raise your hand if you have ever used camel images for decoding images. Quite a few people. Are you satisfied? Yeah, you're satisfied. Perfect. I will show you why you shouldn't be satisfied. So basically, here is camel images source code. It's in GitLab. And you can find this little thing, which kills the performance. What it's doing? Do you remember 15,000 height, image that is 15,000 height? So they allocated 15,000 length tuple, then go in by 15,000 of rows, allocating a string for every row, copying it to another field, and storing the field on the tuple. Should I tell you that this is not looks correctly? I don't think so. So this is actually really, really slow, and this what slows it down. Because camel images, originally I've been like, okay, it's a library from 1999. Some really academical, important people are doing this. And it literally notice that if you don't believe to anyone, always profile, always compare, because even if the superstar wrote the code, it doesn't mean there would be some nonsense that slows your specific use case down. So I just decided to rewrite it in C, and all of the in C. So we did a lot of things to make it faster. So I investigated the decoding libraries, approaches, how to build the libraries to get the most performance. And we did a big array approach. So we use now libspec turbo, which is SMD optimized spec decoding. We use libspng, which is faster than libpng, and we use big array. And on the right thing, you can see that big array. Are you familiar with big arrays? Yes, good. Because unfortunately, I see not a lot of libraries are using big arrays, unfortunately, because it's such an important and such a powerful tool. Basically, on the right side, you can see a C function that allocates a big array, and out of all of the asserts, what it's doing, it can malloc you memory of your size. So you basically, I say, I want this much of memory for my image. It will malloc it for you. If it will throw an exception, OCaml exception, if we out of memory. And then basically it will put it into the custom memory, which will be optimized in terms of garbage collection. So it won't be in the minor heap or somewhere. It will be custom memory, which is mallocked by OCaml and attached a finalizer to it, which is really nice, and it works so much better because this is super efficient. And when you return it and read direct pixels from the big array, it just kills the performance. This allows us to do all of this optimization with raw pixels and so on and so forth. And that's why odiff is actually fast enough. So I just thought that I am criticizing publicly CAML images and I don't provide any alternatives. So I just want to announce that odiff image IO will be soon on OPAM, and it will allow you to use it as a codex, so everyone can just use it instead of CAML images. I will try to make it as fast as possible. I thought I will be able to hack it during the conference, but I was too busy, to be honest. So now let's go back to the history. And yeah, we did this optimization. I was over the moon when I did it. But now we broke the Windows build. And it was a giant story how odiff supports Windows. I do hate Windows after dozens of hours trying to actually cross-compile CAML on Windows. But we actually, yeah, so this was an issue. This was my response, and our one of the core collaborator to odiff, Torben Evert, if I pronounce your name correctly, thank you so much for all of your help. You just did an amazing job. He helped a lot with statically linking Windows, statically doing a lot of work to actually make it on the Windows, and Windows was supported finally. We did resolve it through the giant crutch with Dune configurator reading, but we didn't run in pkg config in the Dune configurator. It was a nightmare, but we did it, and we actually did it through easy. By that time, we deployed every package. There was libpng, but we forked every libspng, every decoder, and manually built everything from source. Gave it to easy because OPAM 2.2 was not existed by the time, and making cross-compilation was only possible in easy or if you're really smart. So we did all of this stuff, and yeah, you can see the pkg configurator still doesn't work on Windows. This is my issue from January 17 of 2029. It's still 2021. It is still not fixed. But we're going towards this direction. So we did all of these things. It was 2021, and we started getting a lot of users. Here are two companies that publicly declared that they use odiff in their production, and that they are super happy about it. I got even some donations. I hope it's for odiff. I don't know really for what, but thank you, Microsoft. And there was tough times. 2022, 2023, we did a lot of work. The project was mostly on hold. I've been fixing some bugs and doing some stuff. But once I realized, literally this year, I realized that my project became legacy. Why? The problem that we've been using all these shiny, glowy things, ReasonML Easy, and Easy now supported by just one person. It has a lot of issues and has a lot of problems. It does not allow to use OCaml v5. ReasonML is not well supported right now. All the libraries I used to run the ReasonML projects on native are not supported for 5 years, no commits. And because of the easy, we also get a lot of Windows build issues. Firstly, Windows build is really slow. It's 1 hour to 1 hour 30 minutes because we built everything from scratch with our own flags. And once Windows version of the Azure pipelines, which was the default CI for easy, updated and it stopped working completely. Then ODog broke the CI of odiff. That was actually a nightmare. And another thing that was actually very scary, that in order to generate this npm release package, Easy creates 13,000 lines of JavaScript to run on post-install script. I knew that it will break sometime, and it actually broke at a FUN OCaml this summer. One time, accidentally, just Windows build stopped working in on people. I didn't do anything. I didn't update. I didn't do anything. I just committed a very minor patch, and then I have no idea for which reason. Likely the minor beta version of ASIA was updated, and we basically got this error where the Unix error pops out on Windows. This is so weird. Then I basically ran my favorite tool. It's R2, by the way, if you want to use this optimizer. And you can see here basically what is it doing for linking packages. It just takes the pass and then calling the pass with Unix create process, which is not resolved correct on Windows because of the backslashes. And it is its own level of inefficiency, because if you use an NPM package, you need to do the fork to run odiff, and then you do another fork to actually run odiff through easy. So what we did is took a lot of effort, and we basically did it this summer. I merged the upgrade to OCaml 5.2, pure Dune, pure OPAM 2.2 Windows support, and VCPKG-based builds, which actually saved so much time. We wrote the sources in OCaml. I rewrote the sources in OCaml, and now we are again a shiny, new, glowy project, which you can take a look at, and it actually implements cross-compiling for Windows. So if you want to take a look how to cross-compile your project for Windows with C packages, just take a look in the sources. It just works on GitHub Actions. Soon we will also provide the native ARM builds, now only for Macs, but soon it will be for Linux and for Windows as well. So it's going to be much more. So what is the conclusion? odiff is the best now. Sorry, that's the fact. Yeah, I mean, it just works. It works pretty fine. It is fast enough. Can we make it better? Yes, we can. The cross-compilation in OCaml is still bad. We don't support like iOS, Android, all of the other stuff. Can we make it smaller? Yes, probably, because currently binaries with OCaml v5 are kind of large. We can make it. Can we make it faster? Yes, significantly. No. Can we make it faster without rewriting it in C or Rust? I don't think so. Will it be faster if we will rewrite it in C and Rust? I don't think you will even notice it, to be honest. But if you want to compete, you're very welcome. Here, oh, sorry. Yeah, I don't want you to compete with me. So here are the things I think will actually improve performance. But just remember that this will improve performance of only 200 of milliseconds that odiff is actually executing from the 5 seconds. So it is something that you can do, or you can test it in a different dimension and make it faster. But basically, that's it I have. That's the story of my project. Here's my Twitter, and this is an actually real camel-based QR code that actually works. You can test it out. Thank you. Cool. Any questions? Sure.
Have you ever tried F-Lambda 2? That's the expecting question, I think.
It's a good question. I've been actually anticipating the question. I've been using F-Lambda, and I have a very spicy opinion that Lambda is garbage. Basically, I can run odiff in a debug build, and it will be the same performance as it is in release build with O3, unsafe, unrolled loops, inline 1000, all of the parameters. I didn't run Lambda 2 though. Maybe it will be better, all of this. Yes, there are inefficiencies, but in the real world, Lambda doesn't help for my project. Likely it will work differently if you don't do this kind of manual loop and rolling, manual flags, manual stuff. But for odiff, you can run odiff in debug mode, and it will be faster than everyone else. Any other question?
You mentioned your single-threaded performance some time in the talk, and I'm wondering, you also migrated to OCaml 5, I think. Did you notice a difference in single-threaded performance between 4.14 and 5.2?
No, actually not. I did. So it was. So basically, it is. It is a nice question. We didn't do proper performance testing between the versions because I accidentally committed the performance degradation and then into the last version of using 4.14, and then I fixed this performance degradation and upgraded to OCaml. So I didn't do the proper tests, but in my thoughts, it was like maybe 3 milliseconds slower in 5.2, something like that. But again, it's maybe just performance measurement error and nothing like that. We need to track much better the performance optimizations though, because we need some kind of CI for that. If you want to build it, please, PRs are welcome, because we sometimes commit performance degradations. People saying that it is slower, and I'm like, oh my gosh, again. No, but actually not as difficult. The binary size is actually much bigger, like 2 times bigger for some reason. The binary executable. But we do commit 3 binaries executable, so I don't know, but they're significantly bigger. Okay, sure.
If you ever want to test regressions, if you ever want to test the regressions on CI, how would you do that? Regressions, like benchmarking of previous. How would you do that?
Yes, this is a hard question because we run the free CI on GitHub, so the load of the machine is totally unpredictable. So I don't know. Ideally, it should be a dedicated machine somewhere running in one configuration, running just odiff CI with performance. So I don't actually know how to do this. So usually I do this right now, manually pulling up PRs and running them, but I'm lazy, so I'm sometimes missing it. Good. I think we are done.